Hello and welcome. This is the AP Calculus AB and BC video for Units 2 and 3 differentiation. These two units have been split up into three different parts. This is the first part, the first video, and we're going to be covering differentiability. With that, let's get started. Alright, so differentiability, what all that really means is if you can take the derivative at a point, and that derivative will be defined. And you can do this if the function is continuous, right? If the function is not continuous, it's not differentiable, never. If the function has a vertical tangent or a sharp turn, we'll define what both of those mean, then it cannot be differentiable. And differentiability is a way to measure a rate of change as well as the difference quotient between two things. Those are two things that we'll continue and learn in the coming problems. But let's get started because as with many things in this course, you learn by doing the problems. All right, so we're asked for the average rate of change of 2 to the x plus 1 over the interval 2, 4. Right, so I can highlight average rate of change. Average rate of change. And if you're kind of confused about how to apply calculus to this, you're not alone because this isn't really a calculus problem. This is more of just an algebra problem, right? You're just plugging in numbers. But the part that is useful for calculus is knowing how to use this for the difference quotient, which we'll cover later. But for this, we just plug in the numbers, right? We go 2 to the 4 plus 1, and 4 is x, minus 2 to the 2 plus 1, and then it's going to be 4 minus 2. And if this reminds you of something, it should, because this is really the formula for the slope of a line. And that's what we're doing, right? We're trying to find the average rate of change of something. Average rate of change. And what does the average rate of change mean? Well, it means if you drew a line between the 2 points at x equals 2 and x equals 4 in here, and you took the slope of that line, that's what the average rate of change means, right? The difference divided by the number of the amount of time that passed, say, if this is measured in seconds or minutes. Now, if we figure this out, right, 2 to the 5 is 32, and then 2 to the 3 is 8. So that would be 24 over 4 minus 2, 2, which would equal 12. Right, so not that hard, right? Just basic algebra plugging in numbers. Let's keep going. All right, so we're asked for the slope of the secant line that intersects the graph of g of x equals 3 to the 2x at x equals 0 and x equals 2. And this whole slope of a secant line thing, that might sound like some fancy wording there, but all that really means is the same thing as this average rate of change, right? The secant line, right? What we mean when we say secant line is if you evaluated this g of x function at g of 0, and then you evaluated it at g of 2, and then you found the slope of that line that you get, right? The same thing we did for average rate of change. And so what we can do is we can write g of 2 minus g of 0 over 2 minus 0. And while this is just obviously a simple calculation of just plugging in numbers because we know this, what we're going to get to is the difference quotient, which is really the same form as this, except that instead of plugging in 2 and 0, we're plugging in two numbers that are infinitely close to each other, right? Say, like, the second one could be 4, and the first one is the limit as you go to 4, right? Like, not quite at 4, but getting there. And that would help us take the derivative. But for now, we're going to use this version of the difference quotient, right? So we plug in 2, and we get 3 to the 4, 81. Plug in 0, 3 to the 0 is 1. So 81 minus 1 over 2 equals 40. All right, let's keep going. We're asked for another average rate of change of this function h of x from 5, that's our first x-coordinate, to 8, our end or second x-coordinate. And we can use the difference quotient again here, right? So we can say h of 8 minus h of 5 over 8 minus 5, right? It's the same thing, right? The nice thing about this form, even though you don't have to do it for everything and it might be a bit more complicated than you need, is that this works for any given function, right? Any function that you're taking the average change of, it'll work, right? You have like the ones that we did above where you had to like plug in the numbers and just find the difference, right? Now that's an abbreviated way, but it won't work for everything, especially complex functions when we have like functions of e, when we have logarithms, when we get into the limits and finding derivatives. So that's why using this form is just better, right? This is more generalized. Now if we plug in x equals 8, that's 1 over 10 minus x, 1 over 10 minus 8, 1 over 2 into 1 half minus, I plug in 5, that'd be 1 over 10 minus 5, which is 1 over 5. Now 1 half minus 1 over 5, I'm going to write it up here in the top. Half minus 1 over 5. Well, what that really is 5 tenths minus 2 tenths. That equals 3 tenths. So 3 tenths, instead of writing 1 half minus 1/5, I can write 3 tenths over 8 minus 5, which is 3, conveniently enough. And that would just give us 1 over 10. Alright, let's keep going. Another slope of the secant line that intersects the graph of f of x at, when it's this function, the square root of 4x plus 1. Our starting x-coordinate is 0. Our ending x-coordinate is 6. You can try to pause the video and figure it out. We've done enough examples at this point, but I will continue on. Right, so it's going to be the same form as 4, right? F of 6 minus f of 0 over 6 minus 0. We plug in 6 into here. 4 times 6 is 24, plus 1 makes 25. The square root of 25 would be 5. We plug in 0, we just get 0 plus 1, that's 1. Square root of 1 is 1, of course. So 5 minus 1, or 4, over 6. 4 over 6 is equal to 2 over 3, and we are done. Alright, next problem. Alright, now we're getting some new stuff. Right, we're told that the tangent line to the graph of f, tangent line to the graph of f at this point, at 5, -7, also passes through 1, minus 1. And we're asked for f apostrophe 5. Right, now what this apostrophe means, that apostrophe means derivative, right? So f, we could say f derivative, the derivative of f at 5. We usually say f prime of 5, right? Now, f prime of 5, that's the derivative of f at 5. Now, how are we going to find that? We're told about a tangent line. Let's see how we can use that. So the tangent line, let's think about it, right? The tangent line intersects only that one point on a curve and nothing else, right? It never hits the graph, at least in the immediate vicinity, which means that it represents the slope, right? It represents the instantaneous slope at that point. And instantaneous slope is a fancy word for derivative, which is what we're trying to find. So really, when they say f prime of 5, we're just trying to find the instantaneous slope at x equals 5. And, well, to find the slope, we need 2 points. And we're told 5 and -7. And we're also told that that same line also passes through 1 minus 1. So we can use our normal slope formulas. right? So that would be minus 7 minus negative 1 in the numerator. Denominator would be 5 minus 1. So that would be, let's see, negative 6 over 4, or negative 3 halves. This is the instantaneous slope, the slope of the tangent line at x equals 5, and therefore it is also the derivative of f at 5. All right, let's keep going. All right, so skip the question. Oops. Now we're asked for the derivative of, asked to estimate the derivative of f of 16, f prime of 16. And I mean, there is no f16 in here, right? There's just nothing. So how are we going to estimate this? Well, let's see. We're told about x equals 15 and x equals 17. And we're given the f of x values for each of these. And if we can find the slope between x equals 15 and x equals 17, that could be the, say, the common slope from x equals 15 to x equals 17, and that would also be this instantaneous slope at x equals 16. Now, why can we do this, right? Now, what we're doing is we're assuming that it's a line, right? Because a line always has the same slope, the same derivative. So if we have a line from x equals 15 to x equals 17, then it's going to be the same derivative the whole time, and we can find f prime of 16 based on the rate of change, which would be the average rate of change, which we have a bunch of good practice now doing since we did it in the last problems. So what we're going to do right now is we're just going to find the rate of change between x equals 15 and x equals 17, and that will give us an estimate of what f prime of 16, the instantaneous slope at x equals 16, could be. Now that would of course be negative 68 minus negative 63, so that'd be what, negative 5 over 17 minus 15, 2, negative 5 over 2 is nothing but negative 2.5, and that is our answer for f prime of 16, derivative of f at 16. Let's keep going. All right, so you had a quick peek of this earlier. But we're asked to find the x values for which f of x is not differentiable. All right, so how are we going to go about doing this question? Now, if you remember, we said that there are only 3 ways for a certain point to not be differentiable. And that was if the function wasn't continuous, if the function had a vertical tangent, or a function had a sharp turn. Now, I think it's pretty clear that at x equals negative 3, it's not continuous, right? We have a jump discontinuity. So at x equals negative 3, that's one of our answers because we are not continuous, so we are not differentiable, right? That's what that's for, not differentiable. Now, we don't have any sharp turns, right? Everything here is all very uniform, right? The derivative never changes, like it never changes drastically. You can always only draw one tangent line, right? If you draw more than one tangent line, you wouldn't have a defined derivative, and that's why sharp turns are not differentiable. But everything here only has one tangent line that you could draw, so there would be no points that are not differentiable due to sharp turns. Now we have to think about vertical tangents, and the one that pops out at me is at x equals 3. Right, that looks pretty vertical to me, right? Like you can draw a straight line there, and yeah, it's completely a tangent line to that point at x equals 3. So there's also a vertical tangent at this point, and that means that we're not differentiable at that point. Since if you try to take a slope of a vertical line, you get an undefined number, right? You get something over 0. Undefined, and that's why we have no derivative, no slope. So that therefore x equals 3 is also not differentiable, and those are our 2 points that are not differentiable. Let's keep going. All right, we have another graph. We're asked the same question. Select all the x values for which we are not differentiable. All right, now how are we going to do this? Well, we can see that at x equals 2, we have an asymptotic discontinuity, right? Infinite discontinuity. So therefore, we're not continuous, we're not differentiable. So x equals -2. Now let's look for some vertical tangents. Well, all of these lines here, right? They all have some kind of tangent line that's not vertical. So we're not going to have any vertical tangents here that disqualify one of these points from being differentiable. Now what we do have are sharp turns, right? And the sharp turn, I know it's kind of hard to see, but it's right here, x equals 2, where we're going up like this, and then suddenly pivot downwards. And the problem with this is that you can draw many different tangent lines on this graph here, right? You can draw a tangent line here, or you can draw one there, or you can draw one like there, say. And you don't know which one of these to take the slope of to find the derivative. Therefore, the derivative could be infinitely many things, and we're not differentiable because there's no defined derivative. That's why at x equals 2 right here, we are not differentiable. So the 2 points that we're not differentiable at are -2 and 2. Let's keep going. Another question. Select all x values for which h is not differentiable. Right, so this time we have the whole function is continuous, right? The whole thing is all continuous, all one straight moving line. Yeah. No discontinuities, right? And that means all of this is going to be differentiable unless we have a sharp turn or a vertical tangent. Now, I don't really see any sharp turns here, right? There are no sharp turns that are happening. The derivative is changing uniformly, and there's always only one tangent line that could be drawn at any point, say here, or here, or here. Now, what we do have is a vertical tangent right here, right? And as we know, vertical tangents, undefined slopes, undefined derivatives, they're not differentiable. This happens at x equals -4, and that is our only non-differentiable point for this question. Let's keep going. All right, same question, different function. You know the drill. You can try to pause the video, see if you can figure it out on your own. Let's look at it for a second before we try to solve it. And all right, let's go ahead. So the first thing that jumps out at me are the discontinuities. We have two of them in here. We have this jump discontinuity around x equals -3, and we have another one. We have a infinite discontinuity around x equals 3, and a jump discontinuity around x equals 1. Both of those are discontinuous. Both of those, therefore, cannot be differentiable. Immediately take those off the list. X equals 3, x equals -3, x equals 1. Don't see any vertical tangents, right? It looks like it could be approaching a vertical tangent here at this asymptote, but this asymptote where it does approach a vertical tangent will be this x equals -3, which we already have. We've already written that down. So we already know that's not going to be differentiable, so we don't have to add anything new. So only thing left are sharp turns, which we can see are right here. That sharp turn here and then here, right? So here we can draw a line there. We can draw one there. We can draw one there. Draw many different tangent lines. None of them are the defined version per se. So at x equals 3, where we have a sharp turn, we are not going to be differentiable. All right, now that is it for the graphs. Let's move on to just dealing with some functions. All right, so we're asked if the function given below is continuous / differentiable at x equals 1. But actually, for the purpose of this question, we're not going to care about this part involving is this function differentiable, right? We're just not going to do that because we haven't figured out how to take derivatives yet, which is going to be the next part. Right? We explore the derivative rules. That's going to be the majority of Unit 2 as well as all of Unit 3 in the next two parts. So we're not going to care about the derivative, the differentiability. We're going to care about the continuity here because we don't know how to take derivatives. So yeah, nothing we can do. Right, now if we had a graph of this, we could look if there's a sharp turn, and that would tell us, right, because there's obviously not going to be a vertical tangent or discontinuity here. If it's continuous, it's not going to be discontinuity, but let's see. All right, so if you remember from last unit, we talked about the three conditions that have to be met to give continuity. And the first one was that, well, three different quantities that have to be equal to give continuity. And the first one was g of 1, right? That has to be equal to the limit as x approaches 1 from the negative direction of g of x. And that to be equal to the limit as x approaches 1 from the positive direction of g of x. Now, on questions like these, all we really need to do is just plug in the x values, right? We're going to find like the limit as x approaches 1 from the positive side and g of 1 are going to be the same number because we have this x greater than or equal to 1, and we're just going to be using this function again and again for both of those. For the one in the middle, where we're less than 1 right here, we just plug 1 into this, and that would be our limit. So we plug 1 in here. 1 squared is 1, obviously. Minus 6 is going to be negative 5. And then 7x squared, 7 times 1, 7 minus 12 times 1, 12. Also negative 5. So this will be continuous. And I guess the answer is just yes. Yes, it is continuous. It is continuous. We'll leave the differentiability for another time when we learn how to find derivatives. All right, another question. Again, this differentiable part here doesn't exist. Not there. All right. So we're asked if the function below is continuous / differentiable, x equals 2. So what we can do here, we just plug in the x equals 2 value for both of these two. Here we get minus x squared is going to be minus 4 plus 3 times 2 plus 6 is going to be 2. Minus 4 plus 6 is 2. Here we have x squared is 4 because 2 squared is 4 times 3, 12. 12 minus 10, also 2. And again, the answer is yes, we are continuous. Let's move on. Right, another question. Is the function given below, continuous / differentiable at x equals negative 4? Right, so yeah, you know the drill. Right, differentiable doesn't exist. Let's plug in the numbers. Give you a second to try it on your own before we do it together. And let's see. All right, let's get ready to do this one. All right, negative 4 squared is going to be 16 times 1/2 is 8. And then x squared is going to be 16. And then 5 times x is going to be 5 times negative 4, going to be negative 20. 16 plus negative 20 is going to equal negative 4. And I think you know that these two numbers are not equal to each other. They're not equal. And therefore, we are not continuous. But the answer is no, we're not continuous at all. Not continuous. So, of course, we're not going to be differentiable, right? And let's move on. Our last question about continuity in these functions, right? I'll give you a moment to look at it. And All right, let's go ahead and see what we have. Plug in 2 squared is 4, minus 4 plus 3 minus 1. Pretty simple. The other one is going to be 2 minus 4, negative 2 squared, is going to be 4, minus 5, it's going to be negative 1. Those two are equal, and we are again continuous. Right. Move on to a different type of question. All right, we're asked which derivative is described by the following expression, right? This expression right here. Which derivative is described by that? And if you've been watching, this is the difference quotient, right? This is just the difference quotient. And let's see what we have here. All right, so we're asked for 1 over 1 plus h minus 1 over h when the limit is as h approaches 0. All right, so this is one type of the difference quotient, right? Now, this type of the difference quotient is where we use f of say x plus h minus f of x over h as h approaches 0, as h approaches nothing. Right, now in the next step we're going to look at the other type, but for now let's look at this. Right, now fx plus h minus f of x over h as the limit as h approaches 0. Now what that should remind you of is the average rate of changes in the secant line we did, except that we're taking between really two close points, right? We have two really close points. And instead of giving us a slope over a lot of points, that gives us an instantaneous slope. We already discussed this, right? This is just the derivative. So we're just putting up this entire equation to find this f of x plus h minus f of x over h, the limit of that as x approaches 0. All we're really doing is asking for the derivative of f of x, right? Now all we have to do is figure out what f of x is, or what f prime of x is, right? Now, let's see. If f of x plus h equals 1 over 1 plus h, and f of x equals that minus 1, well, a function that I see is that f of x, let's erase this prime of here, f of x equals 1 over x. Right, do you agree with that? And we're evaluating that at x equals 1, right? Now, if we put in 1 in there, we get 1 over 1 is minus 1, so this f of x is minus 1, right? And this f of x plus h is going to be 1 over x plus h, 1 over 1 plus h, just like we're shown. So f of x equals 1 over x. And when we've learned how to take derivatives, we would just take the derivative of 1 over x, and that would be our answer. Until then, we can just leave it in this form as the original function throughout the other type of difference quotient. Right? Now, this one still has a limit as x approaches 0, which is kind of uncommon because usually it won't give you that. But in this scenario, it does, and it doesn't really matter. Right? So what they'll usually look like this type is f of x minus f of a over x minus a, and we're gonna take the limit of that as x approaches a. And now in this case, a is just 0, right? That's why we have x minus 0 in the denominator, right? And we're told that f of x equals cosine of x, and f of a equals 1. All right, we're told that f of x equals cosine of x, and f of 0 is 1, right? So it's not an unreasonable deduction to just say that f of x equals cosine of x, right? Because as we take that slope between those 2 points, right, as we get closer and closer to that x equals 1, we're going to be taking the derivative at 1. So we're really going to be taking f prime of 1, or the derivative cosine x at 1. Again, we'll learn to take derivatives in the next video, so stay tuned for that. We will learn all of the rules necessary to take these functions, transform them into their derivatives, their slopes, their rates of change. Stay tuned for that, and I'll see you next time.